Ladies and gentlemen, we are in a pivotal moment in human history. We are far in the reaches of space, far, far away from home. In fact, to show this, if we turn on planetarium mode, that is our sun. It's a little speck in the grand scheme of things. It looks no different from any other star in the night sky. Hello everyone. I'd like to welcome you to this video, and this will hopefully be a series of videos which I'm going to create about the New Horizons mission, which is the probe which NASA has sent, and it's going to be the first probe we send to encounter Pluto. Um, we're hopefully going to learn a lot from it, and this is real-time history. We've never really gotten good photos of Pluto before. So I hope you'll join me and celebrate and try to understand this new revolution which is going to happen. I'm using Orbiter 2010, which is a fantastic space simulator, which is fun to play with. It's immensely powerful, and the best part is it's free. So I'd like to thank all the people who've made Orbiter possible. Well, so what I want to do is I've since a young age, I've been interested in astronomy. I think since I was 7 or something, I got really interested. That was like the start. But, like, I wanted to share my enthusiasm because this is truly a remarkable moment, and I think a lot of people should know about this. So, this is going to be a series of videos using Orbiter 2010, and these are kind of impromptu videos too, because I haven't really assembled any facts. Um, I have some information books around me. I have my background knowledge. I have what research I have done, but this is largely impromptu. So, let's get started. I mean, I really got shocked. I played around with this scenario for a little bit before I recorded this video, and the sun is really so small. Um, it's really hard to believe. So it kind of puts everything into scale. It's like the Earthrise photo, which Apollo 8 took. It really puts it, or the pale blue dot. This really puts into perspective that we are no different from the rest of the universe. We aren't really special in this universe. We are just one part of the grand scheme of things, which, in one sense, is one of the most terrifying things which you learn in astronomy, and in another sense, it's kind of comforting being in a big grand scheme. So yeah, we are pretty far from the sun, and if we are precisely um, 49.40 AU to 29.68. So a major point which I want to talk about is that Pluto is not a planet. Yeah, I know there's going to be some outrage, but I might as well tackle it because we are talking about Pluto, and its distance from the sun varies a lot, which is part of the reason why we don't consider it a planet, but we'll get into that. But it is 29.68 to 49.40 astronomical units, or AU, from the sun. And an AU is approximately the distance between the Earth and the sun, so it kind of gives a more intuitive feel. So yeah, it can go from anywhere between 30 and 50 times the distance which Earth is from the sun. And you'll notice in this planetarium mode that I don't think Earth is visible. The inner solar system is kind of densely packed close to the sun, while the outer solar system is very spread out. And in case you're wondering, uh, find it. Where are you, Pluto? Yeah, here we go. That's Pluto and its moons, Nix, Charon, Styx, Hydra, and Kerberos. It sure has a lot of moons, and before the New Horizons mission, I think we only knew of 3 of them. So by coming this close to New Horizons, it's already discovered 2 moons, and some people have pointed out that it might be a safety hazard. What if there's a moon which we haven't seen yet? But it has a lot of moons, and these are probably captured Kuiper Belt objects. So Pluto is part of our solar system called the Kuiper Belt. Now the structure of the um, solar system is that towards the sun, if I can find the sun, it's very amazing that you can't find the sun without planetarium mode. Yeah, so near the sun, that tightly packed toward uh, close to it is the inner solar system. So you have the rocky planets, Mercury, Venus, Earth, Mars, which we all know about. And then between Mars and Jupiter, kind of the boundary between the inner and the outer solar system, is the asteroid belt, which has a ton of asteroids, as you might guess. And then you have more widespread Jupiter, Saturn, Uranus, and Neptune. These are the outer planets. But beyond that is the home of the comets, the Kuiper Belt. It's kind of like the asteroid belt. It's a kind of big ring around the planetary solar system, and it contains thousands upon thousands of so-called Kuiper Belt objects, and we consider Pluto to be just one of them. And when such a Kuiper Belt object, usually much smaller than, like almost always much smaller than Pluto, um, it's when a Kuiper Belt object like this is knocked out of the Kuiper Belt for some reason. Maybe another Kuiper Belt object hits it, or maybe it's influenced by the gravity of Neptune. Uh, if it's knocked towards the sun, it becomes a comet. The heat warms it, its gases are released, and it forms a tail around it, which forms a characteristic comet shape. So we believe that Pluto is one of these Kuiper Belt objects, undoubtedly one of the biggest ones, but it turns out not the biggest. So uh, we don't really know that much about the Kuiper Belt, and in fact even less about the Oort cloud, which is even further from the Kuiper Belt. And New Horizons is part of an attempt to start to understand them more. So it's a interplanetary probe, and it was launched in 2006. I don't know, I don't think I remember when it was actually launched. I was 4, but I remember hearing about it. I was like excited, oh yeah, we're going to see Pluto, but it was like they said in 2015 we're going to have our closest encounter with Pluto, and I'm like, oh, that's so far in the future. So I'd kind of forgotten about it. But then, there's the hype, oh, they're coming closer to Pluto, it's going to be the closest encounter, and of course I remember, I'm like, oh yeah. Um, so then I got excited. So today is July 13th, 2015, and this simulation is approximately in real time. Starts off at like 12 a.m. on uh, on the 13th today. So it's approximately accurate. So this is kind of real time, and in case you want to know, the closest approach to Pluto will be on 14th of July at 11:49 a.m. or p.m. I don't know, but I'm guessing p.m. because there's also 12. So I think let's time accelerate a little bit because this is a long journey. We're going at 1,000 times real speed, and you can see the time ticking away. You can see that the orbit of the moons is getting a little bit bigger, which means that we're getting closer, of course. So, some quick facts about Pluto. We already mentioned its distance. It can go anywhere from 30 to 50 times the distance which the Earth is from the Sun. Its orbital period, the amount of time it takes for it to do one revolution around the Sun, so like a year on Earth, is equivalent to 248.5 Earth years. That's a long time. So that means that since we've discovered Pluto in 1930, Pluto has only gone 1/3 of its orbit since then. So it hasn't even done a full orbit. So if you lived on Pluto, everyone on Earth would be basically 0 years old. Its length of day is 6.38 Earth days, so this has to do with its rotation along its axis. Um, its orbital speed is 6.1 to 3.7 kilometers per second. Decent. And its eccentricity is 0.25. So what does eccentricity mean? So most of the celestial objects in our solar system orbit the sun, right? And we usually think of orbits as like nice, clean circles, right? But that is not necessarily the case. For most objects, there's a little bit of a stretchiness in that circle. So that stretchiness, how oval-like in a sense the orbit is its eccentricity. So the idea is that an eccentricity of 0 would be a perfect sphere, which technically isn't possible because um, then that means that your horizontal velocity exactly matches the gravitational pull of the sun, which is very hard to do and very improbable as well. And I think there are also some other more physical reasons, but that's 0 eccentricity, and an eccentricity of 1 is basically a straight line away from the sun. So that your circle is so stretched out. If you imagine, do a thought experiment where start with a perfect circle and you're stretching it, and then eventually you'll come to a point where it's just a parabola and it's just zooming off into space. So that's a eccentricity of 1. So most the planets, they have eccentricities which are very close to 0, but Pluto has a eccentricity of 0.25. So it's like 25% of the way to a parabola, and on top of that, its orbital plane, which is like the angle at which it orbits the sun relative to us, is also very deviant from the planets. So that's part of the reason why we have named Pluto to not be a planet. So it might be worth talking about, and I think this was something which I definitely did want to get into, which is like uh there's a lot of outrage on, oh, Pluto's not a planet, how could you do that? But I really want to clarify um why we did this, and I think it is justifiable, and I'll give you some of my reasons. So it was decided by the um, IAU, or International Astronomical Union, which is kind of the authority on astronomy, and it's like measures and weights. Well, not weights, but like the logistics. They're kind of the authority on that, and they decided in 2006, so it's around the same year which New Horizons was launched, that you define a planet by 3 characteristics. I believe that, I don't remember exactly, but I think the 3 were, 1 is that it has to orbit the sun in a roughly, small eccentricity. So yeah, Pluto orbits the sun. Its eccentricity is kind of on the higher side, especially for being a planet. So, kind of fits. Number two was that has to have enough mass, enough gravity for it to hold itself into a spherical shape, or at least roughly spherical. And the idea behind that is that gravity is a central force, which means that it exerts the body which has mass will exert gravity on it from all directions, and it will exert the same amount wherever you are. So what that means is that if you reach a certain mass, um, there will come a point where gravity will pull it into a perfect circle, because if you have an object which has the same amount of force all around it, and that means that it'll eventually have the same radius all around it, so that would be a circle, a perfect circle. But things like rotation, that will change the shape a little bit, but it has to be a good amount of circles. So Earth, Mercury, Jupiter, these are all circles, while compared to an asteroid like Eros, I think it was. That's like a potato shape, and we usually think of asteroids as being kind of potato shaped. So that's the difference. So Pluto actually fits that category, so that's good. The third thing is that a planet must clear its own orbit. So what does that mean? So we have to go back to when the universe was formed. Not the universe. The solar system was formed 4.5 billion years ago, and at that time, the universe was just full of universe. Solar system. I've been spending too much time on cosmology. Uh, so the whole solar system was full of asteroid and comet-like objects. You have tons and tons of small debris from the sun's formation, and it's these which kind of coagulated together to form planets. But and notice that we're getting closer and closer. It's July 13th, 7:55. So now I know that they're using a 24-hour calendar. So that's 5:03, right? That's 2 hours beyond when I'm recording this video. So we're actually pretty close to it right now. Um, Even Sharon has actual dimension to it. It isn't just a point. But you have to watch out, because in this simulation, the closest approach to Nix will be on 14th of July at 11:14. So I'm gonna have to stop the clock for us to witness that moment. So moving on. Yes. So um, eventually, what happened with this coagulation is that it's kind of a race of colliding with each other, bombardment, and eating up as much as you could of the surroundings. So most of the planets, eventually what they did was that they ate all of the um, little objects which was in their orbit. So now their orbits are for the most part clear. But Pluto, as we mentioned, is in the Kuiper Belt, which is chock full of comets and all sorts of debris. So that's where it fails. So because of that, they demoted Pluto, and now it's a so-called dwarf planet instead of a planet. So there was a lot of outrage because Pluto, I don't know why. I think there's been plenty of speculation, but I think because it's so far and so remote, and because it's so mysterious, and we don't know that much about it, and people seem to like mystery. Because of that, I think Pluto's become embedded in our culture, and because of that, a lot of people were not happy with letting Pluto go. So there was a lot of outrage, protests, and all. And I don't think that's justified. I think naming Pluto as not a planet is perfectly justified. And I think um one of the reasons is because it doesn't matter anyway. If you look at in the real universe, and um the universe without humans, just look at the universe as it is, just try to imagine it. There is no such thing as planets or dwarf planets. There's no um natural division between them. They're just different kinds of matter which formed in our solar system. It's just that the consciousness which we are, which is able to judge the universe around us, is it's helpful for us to categorize things. So it's useful for us to categorize things as planets or dwarf planets or asteroids or comets. But in the real universe, of course, there isn't a division. There's no genus or phylum or species in the real world. And hey, look at this. We're close enough to uh, Pluto. By the way, you're going to notice that I'm going to interrupt my talking a lot as new events happen. But we've gotten close enough to Pluto that its mesh has loaded. So in games, especially or simulators, especially in Orbiter, so in the code you have to specify a configuration file which tells the computer that that a planet exists, um, and it gives its basic properties in terms of variables. And then you have to have meshes, which is like the shape of it. It'd be like a 3D model, and you'd also have textures, which is like the surface. It's like a picture of the surface, so the computer knows what to map on the surface. So how it works, because in an effort to save processing power, if you're far enough from an object, like for example the sun or Jupiter, Jupiter has its texture and its mesh, but since we're so far away from it, we just depict it as a point of light. Um, in the game, once you reach a certain distance, the mesh is loaded, and as we can see here, you can tell because it's no longer just a point of light like Sharon. Actually, it's round and all. So that's exciting. Um, we're getting closer, so let's continue. Yeah, so what was I saying? Yeah, our divisions, our divisions or categorizations of objects is purely artificial. So it doesn't mean anything in the real world, though of course, since we are humans, we do choose to care about it because in this interpretation of the world, this is how we view it. But I don't think it matters that much. It's still an amazing system. It's an amazing thing to study. It's quite odd to us. And a lot of people have said that this is very ad hoc, so in a sense, uh, they, the International Astronomical Union just picked and chose certain properties, such as that third qualification, to make sure that Pluto wouldn't make it. But I think it was also a case of uh, since we are in the process of categorization, um, since we are in that process, a useful thing to do to study and see if an object is part of a category is to see if it's so different from other things which we say take for granted that they are in that category. If it's so different from them, then maybe we should reconsider them being part of that category. Makes sense, right? So, by the way, we are now in the early morning of July 14th, and I don't think I'll be waking up for several hours. but, um, but, yeah, because you can think of it that way, and what are some planets which we take for granted as being, planets? Earth, Jupiter, let's take those two examples. So, let's compare them to Pluto. Um, Earth, Jupiter, and basically all of the other planets, they have roughly the same orbital plane, and as I said, that means the same angle at which they orbit the Earth. So, for example, if you might have, it'd be nice for me to have some visuals, but um, you might have Earth and it's orbiting in one circle, but then you might have another object, and this is very eccentric, but not eccentric, but different, weird. You could have another object which is at like a 90-degree tilt. So it'd be vertical from our standpoint. So that's like the orbital plane. So the Earth and most of the other planets have about the same orbital plane, but Pluto has a much different plane. And I might add pictures in this in post, but it's very different. It like juts out, so it's different right off the bat. Another example is the eccentricity, which we talked about. It's um it's much more squat. Its orbit is much more oval-like than all the other planets. And by the way, I looked it up. Um, the axial tilt of Pluto is 119.6 degrees. So, uh, just think about that. Just visualize the protractor, and you have an orbit, which is the rest of the planets, and then you have Pluto, and it's kind of tilted all the way this way. I will put a visual in post, but just try to imagine that it's different. Uh, oh, wrong number. Okay, yeah, I was wondering. 119.6. That's a lot. But it's axial tilt. What that means is it's if you judge north and south, you can kind of tell what the North Pole is and the South Pole is based on geographic and geological things. So, for example, you'll tend to have the ice caps there. So, and you could also study the movement of wind around the object. So, wind tends to go like kind of parallel to the equator, but usually doesn't blow straight north. So, I'm kind of speculating here. I'm not an expert in planetary weather, or weather in general. But you can tell for the most part where the north and south pole of an object is, and you can imagine drawing a straight line between them, which is the axis, and that's the axis on which they rotate. And in fact, I should have thought of this. That's probably the best way to look at where the north and south pole is, right? Because we can look and videotape the rotation of an object over time, and we might even see that with Pluto. Um, and based on that, it rotates perpendicular to its poles, right? So the axial tilt is that, and we can measure the axial tilt uh, with respect to the equatorial plane. So that would be, the equatorial plane is with reference to the equator of the Earth, and the other one is I don't remember the name. Uh, let's see. Let me find the word. Uh, reference. No, I actually need to go to orbit. Yeah, ecliptic plane. Yeah, this is the abbreviation for ecliptic. And ecliptic, with reference to the ecliptic plane, means with reference to the orbital plane of the planets and Earth, which is slightly different from the equatorial plane because the Earth has an axial tilt. So if you measure where that axis is with respect to the ecliptic plane, I think that would make the most sense. Then that gives you the axial tilt. And the axial tilt of Pluto is 119.6 degrees. Um, so there's that, but the actual so-called orbital inclination, so how much it differs from the orbital plane, the ecliptic plane, is 17.12 degrees, which makes much more sense now that I think about it. So, but still, 17.12 degrees is a lot of variation from most of the other planets. Most of the other planets are closer to 0. So it is different, and it is not a planet. Because, as I was saying, um, we can study categorization by its difference from other objects. So, um, how is Pluto so different from other objects? We said that its eccentricity, its inclination are different. Uh, it is a sphere, so that's in common, and other dwarf stars like, I forget the name, Haumea. Haumea is a dwarf planet. It's pretty large, but it is actually kind of oval shaped. So, you can't really consider it a planet in that respect. So, we study at differences, and I think this is a fundamental part of how we do science and how we view the world. Um, we see it differently, and yeah, some people will say, hey, but Earth is very different from Jupiter too, right? But Pluto, that is true, but Pluto is so different from the other ones. It has the orbit is different, as we said before. It's so different that we just don't name it a planet. But that doesn't take away from the beauty of Pluto by any means, and it's a fascinating thing to study. And we are hopefully going to learn a lot. And I think that's a nice segue to talking about the New Horizons mission itself. Let's um, accelerate time, and I'm going to have to keep an eye on the clock because in approximately 8 hours we're going to have our closest approach to Nix. So I'm going to have to keep an eye on that. Uh, let's talk about New Horizons mission. It launched on Atlas D, which is the kind of rocket which NASA uses typically. It's a very typical rocket, uh, which they use for um, interplanetary interplanetary flights. So they use this for Opportunity, Spirit, all of those. And in order to reach Pluto in such a short time frame, you might not think about it. You might not think of it this way, 9 years, but that's really a very short time frame to reach Pluto. It's amazing that we were able to do it. Um, so in order to do that, New Horizons had to leave Earth, escape Earth, reach the escape velocity, and zoom away faster than anything else we've built has. It isn't the fastest spacecraft we've built, but it's the fastest it has an object has escaped the Earth. And then after that, to gain extra speed, it flew by Jupiter. And I'm going to be showing some of these parts of the stages of the mission in more detail in later videos. I want to focus on the Pluto encounter first because it is so important. That's the main thing here. And yay, Sharon has loaded its mesh. Significantly darker, so that tells me that it doesn't have as much ice content. But yeah, so it zoomed by Jupiter, and the idea was to do what's called a gravity assist, which is a very conventional move which you use to increase your speed in interplanetary flight. So, in spaceflight, fuel is expensive. Yeah, it's more expensive than what it was back in like the recession or something. Um, it's very expensive, and it's also very heavy. So, the main thing is that if you're going to take, it's one thing to have fuel, um, which you have to use, and you have to use a lot of it. It's another thing if you're taking that good amount of fuel and you're shipping it to like, you're carrying it with you to like Pluto. So that's a lot of mass, and it's going to take a lot of money to develop the logistics and the technology to do that. So that's the first problem, and the second problem is that to go further, you need more fuel. Makes sense. Um, because there are just more kinds of maneuvers which you have to do. And nice case in point is that you might remember that when we started this simulation, uh, everything was kind of nicely packed together, and everything was like around Pluto, and Pluto was just a dot, right? But now we're at the point where, like, from Styx to Hydra, it's almost covered our entire angle of the sky. So we're very close. And it feels like the Sun and Saturn and Jupiter are even further. See, even Neptune looks like a tiny dot, even though it's so close. Mainly because um, it's on the smaller side, even though it is a gas giant. Um, so yeah, Pluto looks very well defined, and if you've seen artist renditions of Pluto before, particularly the more recent ones, this looks approximately like what you've seen, right? And you might have also seen an image of Pluto, I think I'll put it right here, um, which was based on brightness measurements of the Hubble Space Telescope. So there it looks significantly browner. So that's interesting. And that tells you a number of things, especially that it might mean that Pluto has a lot more ice than what we thought, at least on the surface. So in um, planetary astronomy, we have something called albedo, which is basically a measure of the brightness of an object, its shininess. But if it's more shiny, then it's if it's very shiny, that probably means that it's like ice. If it's middle shiny, it's probably water, and if it's like low shiny, it's probably rock. So we use albedo, and it seems like it has a pretty high albedo here versus this image. Um, so that's a nice thing to point out. And yeah, so back to the gravity assist, right? See, they're going far in the sky, but with the gravity assist, and it's 8:30, so we're close to the Nix encounter. You can see it's getting closer and closer. Let me just check my numbers. Yeah, 11:14. So let's kind of face it. So the idea of the gravity assist is that when you're going on interplanetary travels, uh, the the fuel is very important. So it's expensive, and if you're trying to go this far, then you're going to need a lot of fuel. But because of the added mass, you're going to need even more fuel. So just kind of exponential the amount of fuel you need on a mission. And I think we should take time to look at this because Pluto and Charon and all the other things have grown significantly in size. Look at that. And this makes sense. You might have noticed that what a 10 times time acceleration. By the way, you could have looked at the time acceleration by seeing here, the warp, so 10 times regular speed. You would have noticed that now a 10x, 10x time warp now does approximately what 100 times time warp used to do before. So now that we're closer, the distances seem to go further quickly, right? So, yeah, so as I was saying, um, with the gravity assist, I don't want to miss the deadline, so I'm going at 10. With all of this considered, you do not want to waste fuel. You want to use other means as well as possible. So, it is especially for this reason that rocket science is considered. Oh, you point your engines one way, you push it, you fire your engines, and oh, you're going to reach there. That isn't how it works. It's very careful. It's like an artistic science. I mean, it's rocket science. What do you expect? But you really have to be careful. And a favorite maneuver, which they use, is the gravity assist, where the idea is gravity causes acceleration, right? And acceleration means more speed. So if you fly by a massive object, like, for example, a planet, or maybe Jupiter, Jupiter is a pretty popular candidate for doing such maneuvers, then you can kind of harness that acceleration and it can give you a boost, a gravity assist to push you along in your journey. So that's the path which uh, New Horizons took. So it launched from Earth, it reached Jupiter, gravity assist, and it reached Pluto. Well, about to reach Pluto. Isn't that exciting? It's the mystery is still unfolding. So it's 10:03. So we're almost at that point. I think I'll do real time at 11:13. Well, so that's the maneuver they used, and used casual burns to make like course corrections to make sure you're going in the right direction. But it coasted that way for a good amount of time, and you might have noticed that I said that this was pretty fast. It actually was pretty fast, because if you think about it, the Voyager missions, which were sent to explore Jupiter, Saturn, Uranus, and Neptune, I think they're some of my favorite missions from all of time, because Voyager 1 actually escaped the solar system. I think Voyager 2 is on the edge of the solar system, and we impose this boundary on the solar system, which, of course, as I said, this has to do with categorization, right? So we um, impose this by looking at solar wind and stellar radiation. So all stars, along with emitting light, they'll emit gases, charged gases and charged particles known as solar wind. Might have heard of these when people talk about them interfering with, like, for example, your radio waves, right, or like electronic infrastructure. So uh, these things can happen, and they kind of mark the boundary of the solar system by looking at where the solar wind you get from the sun matches the amount of solar radiation that you get from uh, the galaxy. In a sense, like on Earth, we'll receive solar wind, that's the predominant thing, but we also receive sparse amounts of the radiation from all of the other stars out there. So exactly where the stellar radiation overloads the sun's uh, solar wind, then that's what we've defined as the edge of the solar system. And that's actually quite far from Pluto. I think it's at least double. Um, yeah, so the boundary of this solar system is almost, I think, 1 light year. The solar system is approximately 1 light year across. So Voyager has made it past that, and this is similar to that. And I think Voyager has used, I don't know if he used gravity assist, but to get to the edge of the solar system, it took like 35 years, I think. And uh, Pluto is um, much less than that, but I don't know exactly when they passed the point where Pluto would be uh, past Pluto's orbit, but I think it would have easily been maybe 10 years or something. I'd have to look that up, and I might tell you in the description, or you can look it up yourself. But this was relatively fast. Some people had spent their whole careers on Voyager waiting for the next, or it's reaching Jupiter, it's reaching Saturn, it's reaching Uranus. But we learned a lot from it, and I suggest you research it. And I might do this style video on Voyager. But it is 10:20, so I can accelerate a little bit. So that's the path which it used. And gravity assist had been used before. It's a pretty foolproof and respected process. You might have remembered the other like major astronomical breakthrough of this year, which was the Philae lander, which landed on a comet. First time we've landed on a comet, and which, by the way, would have probably been in the Kuiper Belt area before it came closer to the sun. But they actually used a gravity assist there. I believe what they did was it launched from Earth. It like gravity assisted around the moon, then it gravity assisted around the Earth again, and then it shot towards the Philae lander. I remember exactly, but it did something like that. So it's a proven method, which is used. Um, let's see, what else should we talk about? Yeah, maybe, yeah. Um, Pluto is not the only dwarf planet out there. It has quite a few, uh, members. And, Pluto is actually not the largest of them, which further detracts from it being a planet. Because if there are other dwarf planets out there, which are bigger than it, size is definitely an important factor when considering planets. Not necessarily the only factor, because Mercury is pretty small even compared to like Earth. But uh, it is a factor, and it can be kind of an intuitive factor. But and there's also, of course, the fact that it has to be massive enough to make a spherical size, so that innately has to do with size. But it isn't necessarily specifically that important. Um, but dwarf planets are other um, planet candidates, or even planets like Pluto, which were named um, planets at some point in their uh, at some point in time, and these have been demoted, or they just don't fit the standards, but we don't necessarily want to call them asteroids either. So there's several examples. Most of them are in the Kuiper Belt, actually. Um, one of them is Eris, and Eris is um, its diameter is 26,000 kilometers, while Pluto's is 23,004 kilometers, which is less. Pluto's less than Eris. So this is a shocker, and I think this is one of the things which caused the demotion of Pluto. And so it's larger. It has largely the same composition. So there's that. There's also Make, I think it's called, pronounced, and it's named after an Easter Island god. And I'm gonna increase time warp. There is Haumea, which is the one I mentioned before. It actually isn't that circular. It has a oval-like shape. So there are those, but there is actually one dwarf planet, I think you can consider it, in the Asteroid Belt, so much closer to home, and it's called Ceres. And I think it was once considered a planet as well. It's 10:56, and it seems like we're actually getting kind of, and we're past the orbit of Nix, but we haven't reached the closest approach yet. So at 11:14. Sharon's growing in size too. Turns out that we will be having our closest approach to Sharon after our closest approach to Pluto, which kind of surprises me. But by the way, yeah, notice this blue line? That is the ecliptic plane. Is it? I think it might be the equatorial plane. I don't know. But it's one of those. And up there is the northern zenith and the southern zenith. So where's Nix? Nix. I did not use Nix right before its closest encounter. Where are you? Okay, there. See? Look, it's actually kind of big now. Next one will be this big. And hopefully New Horizons will be collecting data at this point. It turns out that um, New Horizons can't collect data and photos at the same time. It can't take both of those at the same time, so we'll have to alternate. So hopefully we'll get good pictures as well as data, but and also the I'm going to slow down now. We're almost at that point. And I do think that these figures were rounded because all three of these figures. Nix's closest approach is 14th of July, 11, 14, 30, and I think I'm gonna pause this real quick. Control P, because I don't want to miss the pivotal moment. But Pluto's closest approach is 14th of July at 11:49 and 30, and Sharon's closest approach is 12:03 and 30. So I think it's rounded a little bit, but close enough. So we're going in real time. This is our closest approach to Nix. Where are you, Nix? Nix. That's Nix. Oh, I'm gonna pause this. I'm gonna find. There we go, Nix. And 3, 2, 1, 0, and that's our closest approach. And at that point, it was 21,000 kilometers away. So we'll get much closer to Pluto. But goodbye, Nix. Now onward. We set our sights on Pluto. And New Horizons is not going to orbit Pluto. It's only these pivotal hours which we have to get as much data as we can on Pluto, because the fact is, once you accelerate so much as we have with the gravity assist and that fast escape from Earth, it's very hard to slow down, especially because, as we said, to carry that fuel to slow it down to orbit Pluto would be too much fuel. It would economically not make sense. So it's going to fly by, and hopefully it will get a lot of information about the Kuiper Belt as well, in general, and maybe the Oort cloud, and eventually it will escape the solar system, be one with the Voyagers, and I don't know, have the Pioneer spacecraft escaped the solar system? I don't know, but they should have, because they launched before Voyager, but it will reach, and hopefully, because now we have new tech on New Horizons, and it isn't as it doesn't have as much wear and tear as the Voyager spacecraft. Maybe we can know more and more about the edge of the solar system as well with this technology. So Pluto is growing and growing and growing, and this is again loosely an artistic representation. I can imagine that there are new images of Pluto coming in right now, because you might have remembered that I started this at around, I think, 3, so you can go back and try to find when this was reading 3 on July. Well, it would say 15 on July 13th, and you could see how far it was at the time I took this video. So we're actually kind of close, and I think that I don't know that much about the instrumentation on New Horizons, but hopefully it would have had some kind of telescopic ability and have gotten much better pictures of Pluto. So we're getting closer, and I think I'll just look up information on the New Horizons spacecraft. So New Horizons is being operated by JPL, Jet Propulsion Laboratory in Pasadena, California, and they're largely the guys behind some of their greatest missions. As of right now, as of when I'm taking this video, we are 16 hours from the closest approach. So that's pretty cool. Oh, there's actually a nice photo of Pluto now, so I'll post that over here. Look at that. Isn't that amazing? You can actually see, this looks kind of tilted. It doesn't look like it's facing Pluto straight on, but there's like a band like this way, dark band, and it looks kind of bright. It has a kind of brighter albedo on the top of this image. So that's nice. We're getting better and better pictures, which is really, really exciting. So maybe I'll talk about I'm trying to my main idea was that I just show the flyby so that you have an idea of what it'll look like. Um, and also give you interesting facts, but I have a feeling that this is becoming tremendously boring for you all. Hopefully you'll like it, but yeah, we're getting closer, and once we're at our closest to Pluto, we'll be only 12,856 kilometers, which is pretty close. Hey, look at that! It's like a big crater on Charon. That's amazing. So I'll put links to whatever resources on Pluto I can find in the description, so you can learn more in perhaps more interesting way than I've been able to present it. Yeah, we're like half an hour from closest approach to Pluto. Would it be interesting if I did this as like an actual live thing where I actually did it in real time or advanced to Pluto? Would that be tremendously boring? And based on the fact that I'm running out of things to say now, yeah, that'd be something. But so it looks like we're kind of bending around Pluto because we're starting to see more of the night side, and Charon's disappearing. So isn't that cool? Like it's like having foresight to what will happen. Maybe we'll have a little Charon rise. I think I'll just. I wonder how close are we. Like I know the numbers, but what will it like semantically? How close will we be? So you can tell that it's kind of curving around Pluto, right? It isn't going in a straight line as much. And Charon rise. It's nighttime on. Oh, look, Charon is so much bigger now. Isn't that cool? And I'm going to stop the clock, well, real time, because we are 8 minutes away in the simulation from Pluto's closest approach. This will be like when the cocktails are opened and all. I mean, the champagne's open. Too old to know which one. Too young. So just admire that beauty. And the amazing thing is, it's amazing to think that a month ago we wouldn't have had this kind of data or that image of Pluto I had over here. And you can notice, you might notice what seems like some kind of fogginess, like some kind of white fog around the edge. And that's actually because Pluto kind of has a temporary atmosphere. So it happens when it's on its closest to the sun. So it was at that approximately 30 AU. Um, the surface, some of the ice and according to this, nitrogen and carbon monoxide and methane from the surface, which were being frozen, because of the fact that it's like negative 240 degrees Celsius there at its coldest. Um, because of that, when it's at its closest approach, and when it would be at like 218 degrees Celsius, according to this, very big temperature extremes, that nitrogen, methane, carbon monoxide, that would um, evaporate and gravity would hold on to it and it would be a very light atmosphere. Then it goes back out in its orbit through that around 50 AU and all that stuff freezes back. So it's amazing. And it's a temporary atmosphere when it's closest to the sun. That's actually kind of like how the comet tails of comets form, because the materials are kind of evaporating off. So closest approach, atmosphere, then it freezes back and forth and back and forth, which is very cool, I think. Um, so its atmospheric composition is um, 90% nitrogen, and carbon monoxide and methane is 10%. 5 minutes from Pluto's closest encounter. Uh, so its mean density is more towards water than rock. So um, there's different ways where you can kind of infer the kind of materials on a planet or object without stepping foot there and taking samples. As I mentioned, you can look at the albedo, and another thing you can do is that you can try and measure its density by estimating its mass, um, and looking at its volume, and that tells you, and based on that you can get a density, and you can actually look up the mean densities of what water would be, what rock would be, what iron would be, and you can kind of infer from that. And also, like, water looks blue, right? Ice looks white, so you can look from photos what it seems like it looks like, and from that you can kind of infer what it's made of. We think it's mostly an icy world. So, Pluto was discovered in 1930 by Clyde Tombaugh. An astronomer told him in 1929, "Young man, I'm afraid you are wasting your time. If there were any more planets, they would have been found long before this." So, that guy was proven wrong, and proven right, because it isn't necessarily a planet, but Clyde Tombaugh was revolutionary, and he certainly was right. In fact, because of that, Clyde Tombaugh's ashes are in a package which is on New Horizons. So, is that amazing? Like, his ashes are gonna fly by Pluto. Is that amazing? Is that so cool? Like, I just resurrect Clyde Tombaugh and tell him that. Now, Pluto is quite small. To get an intuitive aspect, Pluto would fit comfortably between New York and Dallas. So, uh, isn't that big? Um, we weren't really that sure of the size of Pluto for a long time. In fact, if you look at the headlines on NASA's New Horizons page, it says, "How big is Pluto? New Horizons settles decades-long debate." So, according to this, as of now, like, it has been measuring Pluto and all, but it's also been, zooming in on Nix and Hydra. So, where's Nix? Nix is far away now, right? And Nix and Hydra, I think it was more this way, right? Yeah, Hydra. So it's been zooming on those too, because it has telescopic equipment. And we are 2 minutes from the closest encounter with Pluto. I didn't know we get this close to Sharon. It says here, 29,200 kilometers. And I'd like to congratulate and thank Brian J., who's the guy in Orbit Hangar who developed this so-called add-on. It's like, for all you Minecrafters, this is like a mod. So, um, Orbiter on its own is very powerful, but it doesn't have that much functions. Well, for example, Pluto didn't exist, so it took people um, to assemble, to make these mods to code Pluto. So his mod was based on Pluto, based on add-ons which added Pluto to the system, which added the Atlas 5 to the system, which added New Horizons, and he kind of added it all together. And I'll add links in the description to his to the link for this add-on, and certainly get orbiter. It's free. Don't you like free? So we are almost at closest approach. You can tell the imperfectness of the sphere because in the computer because it's kind of loading pixel by pixel. Be nice if like they did a flyby by daytime. Sucks that they have to do it by nighttime. This is and closest approach. Yay! That's our closest approach to Pluto. Now we're heading further from it and towards Charon. We are 12,856 kilometers from Pluto, and it's pretty large. So yeah, this is the moment when everyone's like, yay! So, in case this might be hard to believe, but that like second took like 6 years of traveling for 1 second. You know, it'd be awesome if we could orbit Pluto, but you have to face the reality in space travel. So we're heading towards Charon, and we'll reach Charon at 12:03. So let's just time warp these 13 minutes. And look at that. I have a feeling we're getting further, aren't we? And Pluto, Charon's actually getting quite big. Since its discovery, we knew about since Pluto's discovery, we knew about Charon. Because it's almost the same size as Pluto. In fact, it's so large that the center of mass of their orbit, Charon orbiting Pluto, is not on Pluto, but in fact in empty space. So what do I mean by that? So when you have gravity, it's usually two masses, right? And usually when we're talking about gravity, it'll be like the sun and the earth, where the earth's mass is basically insignificant against the sun. So because of that, if you can do a calculation, and this is called the center of mass, which tells you based on the mass of the two objects, you can tell where the center of mass, or the average in a sense of their masses, is in their orbit. So usually, because it's like the sun around the earth around the sun, it's usually like in the sun, for example. So the center of mass of the earth and the moon is like in the earth. So that is truly a satellite revolving around the earth. But with Pluto and Charon, it is, you like imagine that beach like Charon orbiting, right? But the center of mass should be like somewhere here, but it's like somewhere here, I'm guessing. So there's actually going to be like a kind of a wobble. It isn't that Charon's orbiting around Pluto as much that they're both kind of revolving around a central point which is between them. So in that sense, it can be viewed more of like a binary planetary system, or binary dwarf planetary system than as like one planet with a bunch of satellites. So we always knew about Charon, but those other moons were only discovered recently, and two of them, I think Kerberos and Hydra, weren't discovered until this final while where New Horizons was the closest thing we had to Pluto. And it seems like night for us on Pluto. It's a little crescent. The sun is very dim. Isn't that amazing? But New Horizons is beaming messages. I think before I close, I want to find information on what kind of instrumentation New Horizons has. So, New Horizons has a variety of instruments, and I think I'll actually get into this more once we have passed Sharon. But, okay, so, get closer, closer, closer. I'm going to stop here. No, a little bit closer. Okay. No. Okay. So in 30 seconds, we're going to have a closest approach to Sharon. Da, da, da. And 5, 4, 3, 2, 1. And that's our closest approach to Sharon. We're 29,200 kilometers away. And as soon as it started, it will end. We'll zoom past Sharon too, and the rest of the system. Far, far away we will go. Our friends for those couple of hours. That thing which we worked 6 years and probably even beyond for is already shrinking like everything we loved before. Now that's an eclipse. It's like sun's just so tiny and Pluto's bigger. And as quickly as it started, it ended. Pluto, Charon, Nix, Hydra, Styx, Kerberos. It always reminds me of Kerbal Space Program. They just fly into the distance yet again. But we still have a purpose, right? We have the Kuiper Belt objects which we have to study. The beauty of space always mesmerizes me. I feel like it's like sunrise on that part of Pluto. I'm going to slow down time a little bit. So let's look at the instrumentation of New Horizons. And then we'll close. There's Ralph, which is like this circly thingy here. This circly, no, is it that circly thingy, or I think it's that circly thingy. You see that thing? That's Ralph, and it's a visible and infrared imager and spectrometer. Provides color, composition, thermal maps. So that's the camera. So it takes invisible light. You might have heard that light isn't just visible light, it's an electromagnetic spectrum, and depending on its wavelength, those very long wavelengths are radio waves, microwaves, then it goes to infrared, and then visible light, that's short fraction of the big scale spectrum, and the visible light is what our eyes can detect, and then beyond that there's ultraviolet light and X-rays and gamma rays, the shorter wavelengths. So this can measure visible light, so it's like any typical camera. They can also measure infrared, which has a lot to do with heat. So that's why I can generate thermal maps, so we can have an idea of how the temperature changes around Pluto. Then there's Alice, which is right above Ralph. It's like right there. Ultraviolet imaging spectrometer. So beyond violet in our Roy G. Biv, right? In the electromagnetic spectrum, we have ultraviolet. And the amazing thing is that being able to detect those other spectrums really changed astronomy, because each wavelength can tell you something totally different. For example, if we look at a star, infrared can tell us about the heat, visible light can give us an idea of what it looks like. Maybe in galaxies, X-rays and gamma rays, they can signify gamma ray bursts, which are which might indicate massive supernova explosions, or X-rays might be caused from a similar event. X-rays can also help you find black holes, because black the area around black holes, the accretion disks, because of the high energies, they can form X-rays. So there's a lot you can tell, and each different spectrum provides you different information. So ultraviolet imaging will give us something, and particularly it says here that it will be used to analyze the composition and structure of Pluto's atmosphere. And it will try to look for atmospheres around Charon and the other Kuiper Belt objects. So that's interesting. Um, whether Charon has an atmosphere, I don't know. It's pretty big. It is big enough to be sort of spherical, so I'm thinking it might have it. And since it's in approximately the same environment, probably is made of approximately the same stuff as Charon, as Pluto, so I don't see why not, and I think that's very interesting to measure. And other Kuiper Belt objects, maybe they'll measure Eris's, that'd be interesting. Then there's REX, which is a radio science experiment. Um, so it measures atmospheric composition and temperature, and it's a passive radiometer, so it's using radio waves, and it also uses studies the atmosphere. Then there's LORI, which is long-range reconnaissance imager. So this is a telescopic camera. So remember what I was saying. We should already hopefully have much better images of Pluto, which I said we do have. Um, because you should have one of you do have the regular camera, and that's Ralph. So that would be particularly helpful in like close encounters, and that would provide the best quality. But I said it should also have some telescopic capabilities, so that when we're further away, um, let's see, how far are we from? You see, they're still kind of far away. So even when we were near Pluto, or even when we were on our close encounter with Nix was still pretty small. So we would use that to measure it. Remember I talked to you about that article where they're also zooming in on Hydra and Nix. So you need that too. So this has that telescopic ability, so it obtains encounter data at long distances. They're also using it to map Pluto's far side and provides high-resolution geologic data. So they have a good amount of time to measure the backside of Pluto because, see, look, we're just looking at it right now. SWAP, and I think this is kind of interesting, solar wind around Pluto. So sounds exactly the way it should. It's a solar wind and plasma spectrometer, so it studies the spectra of objects around it, and so it looks at that kind of rainbow. It splits the light is getting into that rainbow which we talked about in the spectrum, and absorption lines, which are points where atoms absorb the light, and emission lines, which are places where the atoms emit light. Those can tell us what this plasma is made out of. So that's interesting, because each element has its own signature for what emission lines and absorption lines it will create. Measures atmospheric escape rate. So that what that means is that take for example Mercury. Mercury could have easily had an atmosphere earlier on, because just like Earth or basically all the other planets which have atmospheres, um, there was gas around all of them. There'd be gas around it, which would be captured by its gravity and provide an atmosphere. And I believe that Mercury does actually have a little bit of an atmosphere, but it's so close to the sun that solar wind which we were talking about literally strips Mercury from that atmosphere. And this happens to all of the planets. And there are many other factors which can cause this, but especially the solar wind so you can measure the atmospheric escape rate, so how fast that atmosphere is escaping from Pluto. So that's SWAP. And I think I forgot to mention where all of these are. The radio science experiment was here. I think it's part of the radio dish. And SWAP is here, I believe. Yeah, I think so. I'm like approximately pointing based on this diagram. Then there's PEPSI, which is a Pluto Energetic Particle Spectrometer Science Investigation. So that's two S's. And it is right next to SWAP. I think it's this. That's PEPSI. So it's an energetic particle spectrometer. So it's doing the same spectrum thing, but it's looking for energetic particles from maybe cosmic rays. It measures the composition and density of plasma ions escaping from Pluto's atmosphere. So it's kind of like SWAP, but sort of different purpose. Then there is SDC, which is kind of interesting, the Student Dust Counter. So it says, built and operated by students, measures the space dust peppering New Horizons during its voyage across the solar system. So I think that's kind of interesting because it's getting students involved, which is of course the most important thing. I believe in the idea that it shouldn't just be NASA and other people calling the shots. Students should be given the capability to use this stuff and to advance science, because it is the students which are gonna cause the next big things. Maybe you guys will be colonizing Pluto maybe someday. So they also do something like this on the ISS. They have a camera on the ISS which students can use and take pictures of the Earth, which is very useful. So there's initiatives like this, but that's good. And it's measuring student dust, cosmic dust. So there's all sorts of debris in the solar system. There's asteroids, planets can be considered debris too, but you also have that kind of microscopic dust, and that's everywhere. And we don't know a lot about it, but it's interesting, and they're going to be measuring it, it seems. And let's see where that is. The SDC is in the lower deck, so I have a feeling that it's like, might have like a touch sensor or something, and it analyzes any dust which is coming at it. So that dust can vary. Voyager definitely experienced that. Different amounts. I'd imagine that would be much more dust near the Kuiper Belt or the Asteroid Belt, where you have collisions between these debris, which causes even smaller particles. So I hope you enjoyed this. It was pretty impromptu, so I didn't have all my thoughts gathered, but this is an amazing event. If you're watching this relatively recently, watch the live stream. I'm thinking I don't know if there'll be a live stream, but if there is a live stream, you should definitely check it out. If there is, I'm going to put a link in the description, because this will give you an idea of what it will look like, but that will be a truly amazing experience, and that's the real-time thing. So find some way to celebrate it. Remember the dates. Nick's closest approach, July 14th at 11:14. Pluto, 11:49. That's the one you don't want to miss. And Sharon closest approach, 14th July at 12:03. So, appreciate the work which is getting put into this. Appreciate all the science which is going to be gathered. And thanks for watching.